Hello, class 10. The topic that we're going to discuss today is combination of resistors. Now, this is one important topic for you all because based on this topic, you are going to get certain numericals also. Now, starting with the topic, resistors can be combined. Two or more resistors can be combined in two different ways. One is called series combination, wherein you have two or more resistors connected in this fashion. One end of one resistor is connected to the other end of the other resistor. So to say, they are connected end to end, okay, in a straight line. Now, the other kind of combination is called parallel combination, where you can see one is connected to on top of the other, so to say, and the ends of each of the resistor, the two ends of each of the resistor is connected to the same 2 points A and B, as you can see here. The two ends of every resistor is connected to the same 2 points A and B. Now, if say for example current I flows or is coming towards the first resistor, so in series combination what happens is the same value of current I flows through all of the resistors. In series combination, I repeat, the value of the current flowing through each of the resistor, whatever be the number of resistors connected in series, through each of the resistor the same value of current will flow. Whereas if I call this point A, this point is B, this point is C, and this point D, then since the value of the resistances, it's different, as you can see R1, R2, R3 are the respective resistances of the three resistors here, and though the same value of current is flowing, since the resistances it's different, so the potential difference across each of the resistor it's going to be different. So to say, if I say VAB is the potential difference across the first resistor, then VAB is not equal to VBC, that is the potential difference across the second resistor, and of course this is not equal to VCD, which is the potential difference across the third resistor. So in series combination, the potential difference across each of the resistor is different, whereas the current flowing through each of the resistor is the same. Now let's see what is same and what is different in case of parallel combination. If current I comes towards this junction point A, then what happens is this current I is going to branch itself out. So say I1 flows through the uppermost branch, I2 flows through the second branch, and I3 through the lowermost branch. Alright, now the maximum value of current will flow through that arm which has the lowest value of resistance, obviously. Current is going to choose the path, the most easiest path, or the path of least resistance. Okay, so whichever resistor has the least value of resistance, maximum value of current is going to of course flow through it. So we see in parallel combination of resistors, the value of current flowing through each of the resistor, it's different, it's not the same. Whereas since the two ends of each of the resistor is connected to the same two junctions A and B, therefore if we say VAB is the potential difference between point A and point B, then the potential difference across each of the resistor, it's going to be equal to VAB, the same, since they are connected to the same two junctions. Alright, so therefore we see in series combination, same current, different values of potential difference, whereas in case of parallel combination, the different values of current are flowing through the resistors, whereas the potential difference across each of the resistor in parallel combination, it's the same. Okay, so let us now discuss about series combination in detail. We'll talk about parallel combination. Alright, so let me erase this picture for parallel combination. So I hope you've understood this, that the potential difference across the different resistor is different. So if VAD is the potential difference between points A and D, of course, then I can write VAD is VAB, the potential difference across the first resistor, plus VBC plus VCD. Okay, the total potential difference, so to say, across the three resistors in here is equal to the potential difference across the first plus the potential difference across the second plus the potential difference across the third. Now, for convenience here, I am only showing three resistors. Do not forget, we can have any number of resistors connected in series. Okay, so I can rewrite VAD as, now how do I write VAB? I is the current flowing through the first resistor and R1 is its resistance. So therefore, according to Ohm's law, VAB is I into R1. Likewise, VBC is I into R2 plus VCD is I into R3. Or we can write VAD is equal to, we take out I common, R1 plus R2 plus R3. Okay, say this is our equation number 1. Now, what we do is, instead of having three resistors in series connected this way, if we replace these three resistors by a special resistor. Okay, what is special about that resistor? I'm going to talk about that. Okay, let's say we are replacing these three resistors by a single resistor. Let's call it R subscript S. S is the subscript here. Now, like I was saying, what is special about this resistor over here? What is special is, if we let the same amount of current I to flow through this resistor, then the potential difference that is generated across this resistor is the same as VAD, or so to say, it is the same as the potential difference across these three resistors combined in series like this. Okay, so RS is not any random resistor, remember that. RS is a special resistor, in which case, if we let the same amount of current I to flow through it, then the potential difference that is developed across it is the same as VAD over here. If that is the case, then only RS is called the equivalent resistance of these three resistors. Okay, only when the current I flowing through the resistor generates or develops a potential difference VAD across this resistor, then only this resistor is called equivalent resistance. Like I mentioned, it is not any random resistor. Okay, so for the equivalent resistance, or resistor, we can write, what can we write? We can write VAD is equal to I into RS. This is the equation number 2. This is for the equivalent resistance, remember. So, look at equations 1 and 2. So we see that the left hand side of both of the equations, it's the same. Okay, I hope I can erase this. You can pause the video and copy this. Okay, so let me erase this part. Let me erase this part too here. So we are equating the left hand sides. Since the left hand side is the same, therefore we can write I into RS is equal to I into R1 plus R2 plus R3. So I, they divide each other out, and therefore we get RS is R1 plus R2 plus R3. A very, very important equation for you all. So this is the value of the equivalent resistance when three resistors are connected in series. If we have n number of resistors connected, then the equivalent resistance will be R1 plus R2 plus R3 plus dot 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 plus Rn. Remember that. Okay, so we'll come into what other things we can conclude from here. Okay, let me tell you right away. So what we can conclude is from here is that the value of the equivalent resistance is, as you can see, the sum of the three resistances. So the value of the resistance is greater than the greatest value of resistance that we have over here. Say for example, between R1, R2, R3, R3 say for example has the highest value of resistance. Then you can see the series combination of the equivalent resistance in series combination has a value which is greater than R3 also. So Rs is greater than R3 also, remember. Okay, you know this point has an importance. We'll talk about that. Alright, for now therefore, this is all about series combination of resistance, and let us now move into parallel combination of resistance. So I'm going to erase it. I hope you pause the video and copy the things on the board. So I'm erasing this. So now we are going to discuss about parallel combination of resistors. This is number 2. So this is parallel combination of resistance. So let me draw the picture. Let me draw a smaller one. So this is your R3, so this is your R1, R2 and R3, and say this is point A and this is point B. So we've already seen if a current I comes towards the junction point A, then say I1 is flowing through R1, current I2 flows through R2 and current I3 flows through the resistor having resistance R3. Now what we can write is the potential difference across point A, B can be written as VAB, the potential difference across point A and B. So this is equal to I into R1, okay, and we also see that VAB is equal to I into R2, sorry, this is I1 into R1 and I2 into R2 plus I3 into, what am I doing? Also for the third resistor also we can write VAB is I3 into R3. This is what we can write. Okay, but we know I is I1 plus I2 plus I3. We know this. So from this equation, can I write I1 is VAB divided by R1? So since we of course can write that, so instead of I1 we are going to write VAB divided by R1 plus likewise I2 is VAB divided by R2. So VAB divided by R2, and likewise for I3 it's VAB divided by R3. So this is your current. Okay, we can of course take VAB common. So I is VAB over here, and inside bracket we have 1 by R1 plus 1 by R2 plus 1 by R3. And let's see, this is the equation number 1 for parallel combination of resistors. Now the same argument. What we do is, instead of having 3 resistors combined, what we can do is we can replace the 3 resistors by a single resistor. Let's call it RP. Of course, this is also a special resistor, special in the sense that when we let the same amount of current I flow through it, the potential difference that is developed across this resistance is VAB. Alright, so then if this is the case, that is when current I flows through this resistor, then the potential difference developed across it is equal to VAB. Then this resistance is what is called your equivalent resistance for parallel combination. Alright, so I hope I can erase this and this too. So therefore, for the equivalent resistance, what we can write is I is equal to VAB divided by R with a subscript P, and this is the equation number 2. And we again see that equation 1 and equation 2 is the same, the left hand side is the same. Okay, so what we do is we simply equate the two equations, and thereby we get VAB divided by RP is equal to VAB into 1 by R1 plus 1 by R2 plus 1 by R3. So VAB, they divide each other out, and thereby for parallel combination of resistors we get 1 by RP is 1 by R1 plus 1 by R2 plus 1 by R3. So this is the equation that we get for parallel combination of resistors, and Rp is what is called the equivalent resistance for parallel combination of resistors. Okay, now what can we conclude therefore from this equation? What we can conclude is, like in the previous case, we had considered R3 to have the greatest resistance, so to say R1 has the least value of resistance. Now, what we learn is from this equation that the parallel or the equivalent resistance in parallel combination is smaller than the least value of resistance in this combination also. So to say, Rp is lesser than R1 also. To see how Rp is lesser than the least value of resistance R1 also, what we can do is we can see that 1 by Rp, from this expression we can write 1 by Rp is greater than 1 by R1. Since 1 by Rp is the sum of these three, obviously 1 by Rp has to be greater than 1 by R1. So simply cross multiplying, what we get is R1 is greater than Rp. So you'll see that the least value of resistance in this combination, parallel combination, which in our case is R1, is greater than the equivalent resistance in parallel. Okay? Now, what is the use of this? Okay, where is this used? This has wide applications. The equivalent resistance in parallel is lesser than the least value of resistance, also has wide applications. Why? Because see, whenever we connect a television to a socket, okay, or we charge a mobile phone, or we light up a heater, or we use the fan, or we light simply an electric bulb, all of these basically are resistors. Okay, so all the time when we use electricity, be it is simply in lighting a bulb up, okay, so we are using resistors. Now, all of these different connections, electrical wirings that is done in our houses, okay, it's done in parallel. Okay, why? Because since all the resistors are connected in parallel, different wirings, all the wirings at our home, it's done in parallel. So the equivalent resistance of the different wirings and the different resistors that we connect, the equivalent resistance will be lesser than the least value of resistance also. Now, lesser the resistance in the circuit, lesser will be the energy dissipated, because there is something called Joule's law of heating also, that's not there in the syllabus. According to Joule's law of heating, the amount of energy generated is equal to I squared RT, where I is the current flowing, R is the resistance, T is the time for which the current flows through the resistance R. Okay, so greater the resistance, more is the heat energy that is produced. So to say, more is the energy that is dissipated, lost. Therefore, to conserve energy, to preserve energy, all of the connections are done in parallel in our houses. Okay, so therefore I told you this has a wide application, and this of course you need to know. Alright class 10, thank you.